Hello everybody. Can you hear me okay? And is the presentation sharing as it's supposed to?
It is, Max. You're good to go.
Perfect. Okay, so great. This is a bit of a new situation for us. We have never really given guidance on what to expect with an electrolyzer project and what kind of steps and documentation requirements might come towards you. Of course, we understand that people might be located all around the world and that different jurisdictions and regulations may apply throughout. As a disclaimer, we cannot actually provide legal advice or permissions, contribution to the permissions of a project, but we can always provide information and support in terms of integrating our devices to our system integrators. So if you have questions and specific questions to answer from any regulatory bodies and stuff like this, we can help you provide any sort of information from our systems, but specifically providing essentially this proof or a guarantee that permissions are going to be granted, we cannot provide. Okay, so what are we going to be talking about in this presentation? So we'll go over a project definition, best practices for planning and considerations, how to apply these kind of best practices. We've already heard the presentations yesterday from WHA about avoiding different product problems and hazards, and also how to demonstrate that the projects that you're deploying are safe. Then we'll go and talk about the permissions, like what kind of permitting requirements are normal. Specifically in this case, we will be giving examples for decentralized projects in Germany. In Europe, the permitting requirements change from country to country, as well as anywhere else in the world. But the German permitting requirements are quite clear. And so in this way, we can explain a bit more about what exactly is happening there. Then I will be talking about the resources available, and normal obstacles that people may have to cross in order to deploy systems quickly and efficiently. And then finish off with some words on how we are seeing the future in this and how decentralized energy production can help. So, when you start a project, the first thing that will always be the #1 priority is to provide a good project description. You need to really understand the scope of the project. A lot of tenders and a lot of work that is started, especially in pilot projects, there's not a lot of information out there. People will ask you to provide a 20 kilowatt hydrogen system, but their actual use and how exactly those 20 kilowatts will be used is unclear. The combination and integration of different units will have an impact on the overall system operation and hazards that are created, as well as the permitting requirements for each system. So to start with, always start with the basic technical data. What is the project actually going to be used for? If it's a pilot plant, an R&D project, if it's used for testing or inside a lab, a lot of requirements are essentially dropped, and this makes it a lot easier to deploy these type of systems. However, if it's a commercial project, you will have to go through the normal permitting process, and this can be this can really enable people to provide more industrial type of deployments, but at the same time, it can slow down the deployment of these type of smaller systems as well. Understand the required output volume, flow of production. Is this something that where you have to produce a certain amount of kilograms in a day, or you have to produce a quota of hydrogen during seasonal storage and then have to keep this inside tanks, or is it used for compression and refueling? Or is it just straight used for heating? What are the quality requirements of the hydrogen that you're wanting to use? And what are the applications? All of these questions you should try to answer as the very first step of a new project. Then the next considerations will be, where will the system be located? Figure out if there's any external safety considerations. Are you integrating it into an existing system where there might be already some industrial hazards around? What type of environment are you deploying it in? Is it cold? What type of ambient temperature ranges and humidities do you have? Is it near the coast? Do you have to worry about salt water and salty air degrading materials? Who and how would you manage site access and maintenance? Who would go on site to make sure the WPS is continuing to work as intended? And who's performing the access control to make sure that no unauthorized persons are able to affect your systems? Also, if you have venting and draining possibilities, where could you do this and how could you do this? What type of safety considerations are there for the vents? This is all just the beginning of what a project definition requires. But of course, these things, when it comes to the commercial aspect, will become really about the knowledge of these type of integrated hydrogen production systems in itself. So when you go start asking yourself about the sizing. How much green energy is available? Is this grid powered or not? How much storage can you have? Is there limitations on buffer volumes or hydrogen storage in terms of space or in terms of land zone permissions? And these type of things will really impact how your system is built. So for example, if you have a project for heating, but you don't have access or possibilities of storing enough hydrogen, then you will have to increase the amount of possible hydrogen production so that you could, for example, produce the hydrogen and directly burn it in the heater when it's needed. And this can then lower the requested buffer tank or storage tank in between the systems. Alternatively, you could have less electrolyzers and more storage. So exactly how you are balancing these systems is something that is really important to balance well at the beginning of the project and not afterwards, because what you will end up getting to is something that Philip mentioned earlier as well. Sizing the proper buffer volume on the tank will really impact the system lifetime. The more accurate you are with your sizing and with your considerations, the better and lower cost your system will be in the long run. So we can continue with this, talking about the locations. I've already mentioned the external safety considerations and the environmental considerations in a bit. But you also have to focus on the important things. Make sure that the focus of the project is clear. All the necessary considerations are written down. You can also include the project's testability, feasibility, and traceability, for example, in terms of tracking maintenance activities or something like this. All of this is really important for a good project definition and setup. So next up, best engineering practices. This was covered a lot also during yesterday's session in WHA. Health and safety will always remain the responsibility of the operator or integrator. It is very important that you understand the permitting requirements for your local area. In general, at the very minimum, a risk assessment is required. Health and safety requirements and conformity assessments will have to be performed. Sometimes there might be environmental obligations that you have to perform, apply. And also potentially, in case this is a larger project, also perform assessments for environmental impact. In Europe, specifically, we have the Pressure Equipment Directive. So this is, you cannot go around, this is part of the regulation. This must be considered for installation and subsequent testing requirements. You will have pressure relief and safety of overpressure to handle. And those will always come along with specific maintenance requirements. And these maintenance requirements will also change according to jurisdiction. For example, if you have an overpressure protection valve in Germany, you would only have to check its calibration every few years. But in Italy, you would have to actually replace the safety valve with a new calibrated system, and then you could recalibrate the original valve. But those are the type of differences that you might have to consider. In Europe, you also have, depending on how big the project is, other also public processes that you may have to go through that could, for example, control and avoid major accident hazards from dangerous substances. So in Europe, this would be the Seveso directive. And this is only required if you have a hydrogen storage of over 5 tons. So this is normally not the problem in any of our systems. I don't think that anybody has had to use or to apply the Seveso directive on any of our installations. But it's important to note that there is currently no real distinction between a small system and a large system in hydrogen at the moment in most countries. And so this is something to keep in mind when you're sizing systems of certain sizes. Industrial emissions can be also anything from noise to potentially draining the electrolytes and performing those yearly maintenances, and actually being able to dispose of it properly and ensure that this doesn't accidentally go into the environment. And if it could go into the environment, what potential impact would it have? These are the kind of questions there. So best practices, when you apply them, you got to ask yourself, have you done your due diligence? Before you finish the project definition, even, and you start working on the safety concept, really consider, have I thought about the material choices? Am I safe in the way that I've selected and sized certain pipings and systems? If you're, for example, using oxygen, have you considered all the possibilities of hazard reduction for this? Is there any flammable materials or extremely high flow rates inside the pipes, which could cause ignition mechanisms? Have I reduced the number of fittings, just so I can spend less time searching for leaks during the initial commissioning activities? Have I considered vibrations or transport conditions for the units? Are we transporting a container with integrated solutions already? After I've transported it, would I have to retest the leakages on site? And all of these parts are something that you should at least have an idea what you want to do, so that you can communicate effectively with any partner involved in the project, but as well as with the approval bodies and customers. So yeah, from WHA yesterday, they also mentioned leak prevention, ventilation, venting and disposal, which will all have to be considered. Purging, so in this way would be cleaning, specifically for commissioning activities and required site acceptance testing, and leak detection and safety planning. So you start with the prevention before the detection, of course, and this is, of course, coupled with the ventilation, technical ventilation of the sort. How to size it, it always will depend on the units that you're integrating. The EL 4.0 has a leakage rate. Every component and system that you have, so also the stainless steel fittings, which are technically leak-free, they all have a leakage rate that allows hydrogen to come through the seals. These are very low leakage rates, up sometimes in the scale of 10 to the power of -7 millibar liters a second or something like this. So it is extremely minute and won't be detectable with most hydrogen detectors or sniffers. But it's important to understand that even if you have a perfectly technically leak-tight solution, you still have to provide and think about technical ventilation in some way, so that hydrogen cannot accumulate in the room that you are producing it in. So your safety concept. No matter what you do, less is more. Occam's razor, keep it simple, silly. These are all the basic principles that we always push for. No matter what you do, when you do apply the best practices and you're avoiding unintentional mixing, you're anticipating the ignition mechanisms and adapting best practices, the easier the safety concept is to explain, the cheaper it will be for you in the long run to go through the approvals. And it will also make it much easier to clarify how you have finished and actually completed the system of your due diligence. So a lot of times you can refer back to industrial health and safety guidelines. For example, in Germany is the Arbeitsschutz for the chemical boards. If you are interested in producing hydrogen in a workplace, they usually have quite simple safety concepts outlined, which are allowed and which are recommended, but also which would not be recommended. And so I really recommend to refer to your local rules, to your local chemical industrial bodies for referring your safety concept to this, so that you can always say, I didn't come up with the safety concept. This has already been applied in industry over and over. And this will, of course, also help with overall approvals. So permissions. If you look at the map on the right, so this is, I pulled this from the HILO website, which was a project which 15 member countries in Europe, they kind of analyzed the regulatory and framework and barriers of entry into the hydrogen production market. And you can see it is not always clear. So Germany and is especially said as there's no barrier there. But of course there is barrier of entry due to the different regulatory frameworks not being super clear or being quite restrictive in the way that it understands whether one system is small and decentralized or whether it's large. It doesn't really make a distinction for it, but it still becomes clear. It's still clear in Germany and described well what the steps are necessary to take to deploy a system. Other countries in Europe, they don't have it as clear, but it doesn't mean that the barriers of entry are essentially too difficult to do. Of course, always to be noted is that if the application is not commercial or industrial and it is this R&D and laboratory work systems, these are easier to deploy and to push through because they don't apply as many barriers of entry there. So in some countries, so yes, as I said just now, for example, in Germany, you have the BIMSCH, which is a regulation where you would have to go through a public process to get the approval, but you don't need to apply this if you have a R&D system. But you always have to go through building ordinances and land zoning regardless. And with that, it always refers back to your original risk assessment and safety concept. So always will refer back to this, and people will always ask you over and over as to how you have made your system safe and how you've made sure that it doesn't impact the environment. There's tools and resources out there to help you understand better what is actually required to be done. So I recommend websites like hilaw.eu or H2 Tools. H2 Tools is mostly for the American market. HILAW is, of course, focusing on the member countries in Europe. Yeah, but it's something that from place to place, it will really vary. And different barriers of entry are differently difficult to pass. But in general, these are the 4 different barriers that you have in place. So you have the structural barriers. So these are created by non-adapted regulations, which could hinder the deployment of fuel cell applications or hydrogen generators. This is mostly the biggest and most difficult to overcome. because this essentially means that there is no possible way to really deploy something without to actually get approval for certain deployments. Operational barriers or economic barriers in this way are easier to go across. Operational barrier can be resolved by the execution then. So where the legislation does not need to be adjusted, but there is, for example, lacking industrial lacking industrial standardization of the implementations for these systems. So this will be the case in a lot of countries which refer to European or international norms to fill their own regulatory frameworks. So this is something that can also actually help you be able to deploy systems in certain cases, but it's something that has to be checked in a case-by-case basis. Economic barriers, of course, sometimes, especially the public processes, and when you have larger installations, there will be the permitting process that takes some time. This always is associated with some cost, and the technical approval of these and checking of these systems will always be expensive. And then, of course, there's regulatory gaps, and this is defined as like the absence of a specific regulation on a topic, and this can create uncertainty about the applicable regulation, whether it's not properly harmonized or aligned. It doesn't make too much difference. In the end, all of these barriers can be overcome, but it is something that will really vary from project to project. So, where are we going? What's the outlook? Where is the future of green hydrogen and decentralized energy production? Again, the regulatory framework is very different from each jurisdiction. And as with any change of regulation, the timeline is always 6 months from now if you ask the politicians. But more and more people are getting involved and getting on board with green hydrogen production. It's in everybody's best interest for us, we believe this, to lower and streamline the barrier of entry to allow hydrogen economies to flourish around the world. And it is our general wish that green hydrogen production projects with a capacity below 2 megawatts are entirely exempted from environmental permits, as a specific risk or threat to the environment, in that case, can be really well contained and accounted for. Actually, as a wish from Enapter in a way, would be great to understand that if you could measure the climate benefit of replacing fossil fuels by green hydrogen, and you can account this in your projects, this could really, really help showcase the difference that green hydrogen projects can make in the world. But sadly, so far, no country in the world does this. But if you're really thinking about it, it's totally different whether you're deploying the next chemical plant or projects that helps fight climate change. So we believe that this is something that could be accounted for. Okay, thank you for your attention. And if you have any questions about this or something like that, reach out to support@enapter.com. We will help you as much as we can, but of course, it's something that we have to do case by case. Thank you. So I wonder if there was any questions.
Yeah, Max, thank you very much for the presentation. I think that was very insightful for people to see what points they should consider before starting a project and while implementing a project. So far, there were not any questions related to this yet, so everybody was paying very close attention to what you were presenting, I think. But does anybody now have a question related to the points that Max discussed? So still your chance to ask a few questions.
Okay, I guess all the questions were answered then. Happy days. First time presentation and great. Okay, I think there's a small break in between now and the next session.
So yes, so we are starting the next session at 10:20. So we would have a 20-minute break now. If we were to go into it, there were still quite a few questions from the integration tips and EL 4.0 deep dives that were still unanswered. So we can also answer those after the partner session if you prefer, Max.
Oh, I can answer them now as well. I don't mind.
Sure. Let's bring then Philip back in.
I'm back.
Fantastic, super guys. So yeah, quite a few that were still unanswered. So maybe you want to go through a few of them while we still have 10 minutes before going on break.
Yeah, sounds good.
Thank you.
Maybe Jens, you can read them out. Is that possible, or Max? How should we do it?
Yeah, I can answer them, and you can ask me, or we can ask each other back and forth. I don't mind. We can take it as we go.
Okay. Then I will start with a question. Is the water tank equipped with a level sensor?
Oh, right. Yes. Yes, it is.
Okay. Then, yeah. What is the life of an electrolyzer for all conditions being normal in normal wear and tear, effect of humidity, corrosive environment, and water quality unit in years or hours of usage? So this is again about the lifetime under normal conditions and the effect of humidity and corrosive environments.
Gosh, please repeat the question.
Okay, so like before we were talking about the 35,000 hours operation time.
Sure.
Now, when we consider a very humid or corrosive environment, for example, I don't know if this is part of the question, but when we're considering setting up an electrolyzer in the middle of the ocean on a ship or something like that. So we have, for example, salty air, or we have a very humid air in tropical regions.
Right.
What needs to be considered here?
Yeah, of course, our electrolyzers are actually certified to be used in quite a wide range of ambient temperatures and humidities. But we don't know the exact effect or impact of salt water on or salty air on our systems. We do have, we've of course considered very heavily any sort of galvanic corrosion inside the units. So even if there was, a salt deposition on the surfaces of the metals, most of our parts are made from from stainless steel parts, which won't be as affected. Furthermore, actually, our units have a production, output pressure of up to 35 bar, right? But the tubing and pipings for the standard stainless steel piping is actually rated to over 300 bar. So that coupled with the fact that we're using, stainless steel 316L, and there's a very, very large safety factor on the actual implementation of the system, we essentially don't expect an impact on the system or the overall system lifetime in any sort of way for these type of different deployments. But of course, impacts on the electronic boards or something like this need to be considered.
Okay, thank you. Then the question about how do you exhaust the heat generated from the AEM process? Yeah, I think we already talked about that, the liquid-cooled version, the air-cooled version. So yeah, I think that's pretty clear. Maybe what about this one?
There's a hydrogen requirement of fuel cells 3.0. Will the 4.0 require a dryer? I think this question, have we answered this already?
Yeah, I think maybe we talked a little bit about it. So yeah, the purity of the hydrogen increases from 99.9% to 99.99%. So we are actually having the hydrogen 5.0 coming out of the dryer, and this is sufficient for the fuel cells, at least the ones that I know. Do you know any fuel cells with higher requirements, Max?
No, but I think so. The main difference is that actually most hydrogen that is deployed, is actually right now coming from gray hydrogen, right?
Yeah.
And so there's lots of other contaminants inside, and the fuel cell hydrogen quality standards, they usually refer to most other contaminants to be within the hydrogen 3.0. But technically, our electrolyzer would have too much water inside for most normal fuel cell quality standards. However, I think this can be managed also specifically by the way that the system is integrated. Most fuel cell manufacturers, if you contact them, they will actually not be against having a little bit more water inside their inputs, but it's very important that there is no liquid water inside. And if the dew point of the produced hydrogen, changes due to the output pressure that you have, you could have some liquid condensing inside the lines. And I think the main point would be that, yeah, technically you could use the hydrogen directly from an electrolyzer, but it would be recommended that this is checked very, very carefully, and that there is good filtration of liquid water before the input of the fuel cell, and that this is also checked with the fuel cell manufacturer. But technically it's possible because the rest of the hydrogen that we produce is extremely pure.
Okay, maybe talking a little bit about the dew point. Yeah, I didn't mention that in the integration tips, but yeah, what devices can you actually use downstream the dryer, for example, yeah, to measure your hydrogen quality?
What do you do to measure the hydrogen quality? Downstream?
With a dew point sensor, for example. Yeah.
Sure. Yeah. Yes. Dew point sensors. There's several technologies out there, and different methods of how it's done. So some customers, and especially industrial customers, require monitoring of the gas quality that is being produced. But of course, this has an impact on overall system efficiency. So you really have to balance, or you should look at balancing the impact of constantly sampling hydrogen or potentially spending more on direct inline measurements. So you can, for example, compensate dew point measurements according to pressure, but you need to do some extra calculations on this, and yeah, it might be increasing the demands on overall system control and yeah, and monitoring purposes.
Okay, thank you. We have some more questions regarding the temperatures. So, for example, yeah, in the previous presentation, I said the oxygen coming out of the O2 vent line can yeah, reach up to 200 degrees, but this is really the maximum. Maybe you can talk a little bit more about like average temperatures, and then as a second question, also what are the temperatures from the H2 vent line or the H2 out?
Okay, so let's start with the oxygen vent of the EL 4.0. So it's at maximum. So in case the system is essentially running into error modes, and there is potential, the recombiner is really performing its safety function at that point. That's at that point, the output would be 200 degrees Celsius. In general, the output of the vent line would be at around 90 degrees Celsius. But of course, this is still very hot. People should be careful when operating these systems. Normally, there's some sort of, even on indoor applications, the people have usually got some sort of protection in front of the electrolyzers, some sort of mesh or something like that stops people from being able to touch it. This could be enough of a hazard mitigation for accidental contact with the vent lines, for example, so you don't burn yourself. But I would recommend that some heat-resistant insulation material is placed around the exposed parts in the front panel of the vent line. Everything in this regard is actually quite easily manageable, and it also helps with the management of the condensing liquid, because essentially with the extra heat that's coming out of the system, you will be able to streamline the placement of the water trap a bit more, I think. And then hydrogen, the hydrogen bent output temperatures, of course, depends a little bit on the ambient temperature of the system, of where the system is deployed at the time. But it would be limited to 55 degrees Celsius because, of course, that's the maximum output temperature of the actually produced hydrogen as well.
All right. Thank you very much. Now we have 2 minutes left, so maybe a last question would be possible. Let me check which one could fit. Yeah, there were also some questions that we already talked about a little bit. Maybe
unstable power supply. Yeah, so what does unstable power supply have impact on the ER 4.0? Any recommendations to be considered upstream powered switchboard design such as UPS? So it depends on your on the stability of the voltage that you're supplying to the systems. All of our electrolyzers have their own power supply units. Of course, they are commercial components. So it is the same as powering any sort of equipment with fluctuating input voltages. If you do this, it can happen that the power supplies go into protection mode or error mode, which would then result in the system shutting off. And this is technically not a bad thing. It is something that you should avoid, but it's part of our safety functionality that in case the system has any, in case of like large leakage detections in your installation room or something like this, and you need to make the system safe as fast as possible, simply remove the power. So this is one of the most general ways of reducing the hazard in the installation, is to be able to remotely and also automatically cut the power in case any hydrogen concentration rises. So it is normal to be able to cut the power as such. And so a UPS is not always required, but it can be used in case the voltage is very unstable.
All right. Thank you very much, Max. Yeah, it's now 10 past 10 here in Central Europe time. And I think, Jens, what do you think? It's time for the break, right?
Yeah, I would say I would thank both of you for going through additional questions, and then we are having a short break. And after the break, we will come back to meet some of our certified integration partners who will showcase how they did some of the installations, which hopefully will be very insightful for other people as well. So Max, Philip, again, thank you very much.
Thank you, everybody.
You're welcome. Thank you.